Hi, today I want to explain about how to calculate the spectrum of an exponential signal using discrete time Fourier transform. So now we have a signal in time domain, discrete time domain, and our exponential signal. So here A is a number that its magnitude is lower than 1, and U here is the unit step function. So it have 0 when n is negative and 1 when n is 0 or higher. No, yeah, 0 or higher. Now we want to calculate the spectrum of this signal, which is normally denoted by X, E, J, omega. In some books, they are using a big omega to describe the frequency of a discrete time signal. As we know, the equation of Fourier discrete time Fourier transform is like this. And from minus infinity until infinity, xn e minus j omega n. And some books, they are using big omega here and also big omega here. It have the same meaning. So by knowing that, we can directly put our xn, our signal, to the equation. Because our xn have a unit step function here, so we can change the border or the threshold of the sigma accordingly. So now we change from 0 until infinity, and then we change the signal into our exponential signal and then continue with the equation. Because now we have n here in both of the factor, we can combine it. And then we can use a sigma equation to solve that, which we have here is from n from 0 until infinity, alpha exponential by n is equal this when alpha is lower than 1. Now we put this equation into our spectrum, and we have this. This is already our spectrum. However, it is often happen that we need to separate the magnitude and the angle of this spectrum. For that, we need to remember the equation for finding magnitude and angle for a normal complex number. For example, we have here a complex number R, real component, imaginary component, and then we can calculate that the magnitude of this complex number will be square root of real square and imaginary square, and then the angle is arcus tangen imaginary divided by its real. If we have another complex number, which is in this relation, the magnitude will be equal with dividing it the same, and then the angle will be the minus of the other angle. And for calculating the magnitude and the angle, that's why we need to separate this polar form into a rectangular form. For that, we can use the simple equation from exponential. As you might recall, I make a more general one, j theta cos, and then the sign is following this. Yeah. So using that, we want to make this equation into a rectangular form. Minus and minus again, and j a sin omega. Yeah, so here we have the real part and the imaginary part. Now, to calculate the magnitude, we can use this equation here, and we have real part plus imaginary part. Yeah, we can a little bit simplify this equation by doing so. As you might recall, a plus minus b quadrat is plus b. So using this, we can change this equation into 1 minus 2a cos omega of course it goes until here. This is also and this one we can also simplify it, maybe from here better, with the knowledge that cos quadrat theta plus sin quadrat theta is equal to 1. So this part become a square. So then we can write down that the magnitude of the spectrum is here we have the magnitude, and then to continue we want to count the angle, and for that we use this equation, that is the when we have this relation, so it's to have minus here, so it's minus arcus tangen imaginary part, we look at here, divided by the divided by the real part. Yeah, now, so with this, we have both our magnitude equation and our angle equation. In some cases, we want to know the value of a specific frequency. For example, we want to know what happened with the magnitude and angle when the frequency in omega is 0. We can simply put the equation in the equation here. So the magnitude when 0 is, so cos 0 is 1, and therefore we can put this. And using the equation here, we know that this is equal to a minus 1 square, and therefore we can even simplify it as something like this. And for the angle 0 here, so since 0 is 0 and 1 minus a, yeah, which is equal to 0. So now we have our value in a certain frequency. To imagine how this graph look, it is easier to use a graph plotter or generator. In this case, I want to use a free website to sketch this graph. Here I'm using a website for doing it. I put my a here, a number that is below 1 and is positive, and then I put the equation of the magnitude, which generate this blue function, and then I put the equation of the angle, which generate this purple function. The Fourier transform of a discrete time signal is always repeated, or it's periodic for every 2p, which is around 6 here. So it's always repeated. The low frequency of this signal is represented by the function value around 0, and the high frequency of this signal is represented by the function value around p, or around 3. In this case, if we change our a, it will have higher lower frequency, so it's stronger in the low frequency compared with the high frequency. If we change the a value into negative, this will have a different effect, which we can see here, that this signal have higher or stronger high frequency component compared with the low frequency component. This makes sense because once we have an A that is negative, the signal will have an interchangeable sign. So it's like positive, and negative all the time, and that makes the high frequency of the signal become very strong. So this is what I want to share today. I hope this explanation will help you in learning discrete time Fourier transform. Thank you for joining, and bye.